Okay, this is example 18, and this is telling us that a fair cubical die and a fair tetrahedral die are thrown. The discrete random variable s is defined as the sum of the numbers on the two dice. Okay, so for letter A, we're asked to construct the probability distribution of s as first a table of values, a bar chart, and then a piecewise function. Okay, so before that, okay, just looking at the way they presented it, okay, notice that they first created a sample space. Now, why is that? It's easier to see all of the possible results, which you will later need. And so you do that by creating a sample space, especially when you don't have a function provided. Okay, you're just given a situation. You kind of have to really see what are the possibilities. Okay, and in this case, you have two dice. Okay, and the first one is cubical, and then the second one is tetrahedral. Now, in case you didn't know that, okay, you should be aware that a cubical die has 4 sides, and a tetrahedral is another way to call it a 6-sided die. Okay, so given that you have two dice, okay, you roll them. What are they telling us to do? They're asking us to get the sum of the numbers. So this part, this rule that they're going to throw, whatever that rule is, that will define what numbers you're putting in your sample space. Okay, earlier, if you look at example 17, they gave us a function. They told us, I'm only using values from 3 to 7. Okay, they were very clear mathematically telling us what the rule was. But another way they can test you is by telling you, just giving you a situation and telling you what, how are they going to get the result. In this case, it's defined as the sum of the numbers. So obviously, to get the sum of the numbers, you need to add them. All right? So to create a sample space, you list one row. In this case, the row is for the tetrahedral die. And then the column is the corresponding cubical die. Okay, and then let's say I got a 1 and a 1. What would I do? Well, according to the rule, I will get the sum. And so 1 plus 1 is 2, and that's how they got 2 in the sample space. And you keep doing that for all of the possibilities. And just by looking at your sample space, you can already see that the lowest value is 2 and the highest value is 10. Okay? So now that this is established, okay, we can proceed with the table of values. Now, here's the table of values. Notice that they're only ranging from 2 to 10. Again, the reason why this is only from 2 to 10 is because in my sample space, according to the definition or what they've defined for us, okay, the only possible values that I should be able to get would be from 2 to 10. Okay, if you have 1 here, that will be incorrect because there is no way that I can add a number from a cubical die and a number from the tetrahedral die and get a 1. Because in these two dice, okay, the numbers only range either from 1 to 6 and 1 to 4. All right? And then, of course, the highest value is 10. So your value should only range from 2 to 10. Okay? Notice how they labeled the table. Again, the variable we're using here is s. So the lowercase s goes here. And then rule of thumb, like I mentioned in my previous videos, just put the capital P for probability. The variable capital S equals the lowercase s. Okay, this is just standard. Just remember that that's how you write it. Okay, now, filling out the probabilities. Well, how did they get 1 over 24? Well, 24 came from the total number of possibilities. Okay, excluding this blue or purple part, if you count all of these squares or simply multiply the length and the width, you'll get 24. That's how many possible combinations you can have. Okay, so that's there. Now, out of the 24 possibilities, how many times could I possibly get a 2 as the sum? Why am I focusing on the sum? Because that is the rule that they're giving us. Okay, so how many times can I get a 2? Well, you can only see 2 once in this sample space, so that becomes 1 over 24. Okay, how many times do you see 3? You only see that twice, so that's 2 over 24. Okay, and so on. Now, in case you're wondering where did this 1, 6 come from, they simplified it, and in a moment you'll see why that makes sense, okay? But there's a reason why your numbers are the way they are, okay? Again, this is just how many times does the number appear in the sample space over the total number of possibilities, which is 24, okay? So that is for the table of values. For the bar chart, this is again fairly similar to the previous example. Okay, if you have your table of values, creating the bar chart is easy. This first row just goes in the x-axis with the corresponding label, and then this second row goes in the y-axis. Convert it to a decimal for convenience, and then just draw your bar graphs accordingly. And notice how they labeled the y-axis too. They just strictly copied off what we put here and put it there. Okay. All right. Now I will spend more time discussing the piecewise function. Okay. For the piecewise function, first of all, you need to recall what a piecewise function is. Okay. It's basically a generalization of the specific values that you have, so that if you go back to the rule, okay, you would be able to go back and get the specific answers from the table, right? So I'll just copy what the answer is, and then we'll just kind of work backwards so that hopefully this will make more sense. Okay, so in this particular piecewise function, we have 3 groups or three possibilities, and sometimes you might have more than 3, or you might have 2. Okay, it really depends on how you'll organize your data. Okay, then here where your S is an element of a natural number. Okay, so this is the established rule. Now looking at this, the easiest thing to kind of explain here would be this middle part. Now earlier, if I go back to the table, notice that from 5 to 7, my answer is always 1/6. Okay, and they simplified it for a reason, so that we can establish that generalization that if my S falls from 5 to 7, the answer will be 1/6. And that's exactly what this part is saying. That if S is from 5, 6, or 7, the answer is 1/6. Okay, so we're done with the second part of this piecewise function. Okay, now let's go to this first part. The rule they're telling us is that if my numbers go from 2, 3, and 4, if I input those values for S into this rule, I should get the values in my data table, or in my table of values. So take note that for 2, the answer should be 1/24. For 3, the answer should be 2/24. And for 4, the answer should be 3/24. So if I check that using this rule, if I substitute 2 into S, okay, I indeed get 1/24. Okay, if I substitute 3 into S, okay, and then I follow the formula or the rule, I indeed get 2/24. And if I substitute 4 into S, I will also get 3/24, which matches what I have in my table of values. So this generalization is correct. It will work. It will be valid. Okay, and same goes for this third rule. Okay, if I'm looking at numbers 8, 9, and 10 from my table of values, if I put 8 here, okay, 11 minus 8 is 2. Sorry, no, that's wrong. 11 minus 8 is 3. And then 3/24 is indeed the corresponding value for 8 in the table of values. Okay, same goes for 9, same goes for 10. So as you can see, by working backwards, this is supposed to be a generalization for the numbers I'm getting. Now the question and the main problem is how will you do that? Now, that takes practice, okay? If you look at this one key observation is you always relate, okay, one way to do it is you'll relate your s, your lowercase s, and to any number in the second row. So for me, what I'm noticing here is if s is, let's say s is 2, right? My numerator is 1. If s is 3, my numerator is 2. If s is 4, my numerator is 3. So what's the pattern? What's the relationship? The numerator here always happens to be 1 less than that particular s value. And so that will kind of help me decide and figure out that maybe the rule should be that s minus 1, and that should give me my answer for numbers 2 to 4. Okay? Why is it 2 to 4 and not 2 to 5 or 2 to 6? Well, you can check that if I go to 5 or 6, the rule will no longer give me the right answer. And so that tells me, okay, I have to stop at 4. Okay? For numbers 5, 6, and 7, okay, there's no need to create some special rule because they have the same answer anyway. So go ahead and just keep that answer and say, if I'm from 5, 6, and 7, my answer should be 1, 6, regardless. Okay? And then for the last part, 11 minus s. Now, notice again the relationship between s and then, in this case, the numerators, since the denominators are all the same anyway. Okay? How do I go from 8, okay, because that's my range, from 8 to 3? Well, I could say, well, what if I did s minus 5, right? If I did s minus 5, okay, I'd be able to get 3. But s minus 5 wouldn't work for the next numbers, right? So you have to be creative. It might have to be trial and error from time to time. But if you notice, if I do 11 minus 8, that gives me 3. If I do 11 minus 9, that gives me 2. 11 minus 10, that gives me 1. Okay, normally the numbers you'll be using to establish the rule won't be far from the relationships you should be able to observe in the table. Okay, but don't limit yourself to simply addition, subtraction, because sometimes you might have to multiply. But again, it takes practice to get used to figuring out patterns or generalizations. Okay? All right, so moving on to letter B. Now, this is going to be a long video, but I'll just finish it in one go. All right, so that's for the first part. For letter B, now we're asked to find the probability that s is greater than 2. Okay, so I think I'll just use my book here. More efficient. Okay, well, I already know that my values must be greater than 2, right? Or 2 to 10 at least. So I don't have to worry about the probability of s being greater than 1 or the probability of s being equal to 0 because, okay, I'm already starting with 2. Okay, that is the number I'm starting with. So if I know the probability of getting a 2, then the probability of getting a number bigger than 2 is just the complement of that, right? The probability of getting a 2 is 1 over 24. So the probability of getting something else that's not a 2, and the only possibilities here is greater than 2, would be 1 minus 1 over 24, and that will be 23 over 24. Okay? Now, how about this one? What is the probability of getting s that is less than or equal to 6? Okay, well, that means I'm only going to look at numbers that are 6 and below. And so that means I'm only focusing on this part. Okay, so 1 over 24, that's from the probability of getting a 2. 1 over 12, that's the same as this one, they just simplified it. Okay, 1 over 8, it's the same as this, again, they just simplified it. 1 over 6 and 1 over 6. Okay, why did they stop here? Because all I want is PS less than or equal to 6. Okay, and then that's my answer. Now, for the third one, this is again conditional probability. Okay, by the way, take note, when they say S at most is 6, at most is the same as less than or equal to. Okay, now going back to this, the probability that S is at most 6 given that S is greater than 2. Well, we've already figured out both of these answers, okay, the probability of S greater than 2 is 23 over 24. The probability of S at most 6 is, according to this, 7 over 12. Okay? So, how will we do this? Okay? Well, you just have to follow the rule that we've established earlier. And in case you forgot, the rule for conditional probability is the intersection of both divided by the probability of the given. So in this case, I have, okay, if I were to translate this, okay, following, if this were to be A and this were to be B, what would this be? Okay, this will be the probability of S less than or equal to 6 intersection S greater than 2 over the probability of S greater than 2, right? Well, what is the probability that S is greater than 2? From the previous problem, we know that that is 23 over 24. Now, the only problem we need to figure out now is what is this part, okay? What is the intersection between S less than or equal to 6 and S greater than 2? Okay, well, I could rewrite this. Okay, what is an equivalent expression for this? Okay, now let me just write it before I explain. Okay, now the question is, how are they equal? This and this. Well, first of all, S greater than 2, okay, is also equivalent to S greater than or equal to 3. Okay, let me say that again. If S is greater than 2, that is equivalent to saying that S is greater than or equal to 3, right? Because if you're greater than or equal to 3, that means that your values can be 3, 4, 5, and so on. If you're strictly greater than 2, that means you cannot include 2, so you will have to start at 3 anyway. So, and then here we're saying S is less than or equal to 6. That didn't change. S is still less than or equal to 6. So why did we rewrite it this way? We rewrote it this way so that it's easier to see, okay, or compare the numbers that I'm looking for. All right. So here I'm looking at 3 all the way to 6. All right. 3 all the way to 6. All right. And if you get the intersection, okay, you should get 13 over 24. All right. And so if you have the two fractions, it should simplify. Cross out those denominators. You should have 13 over 23. Okay. So for this one, please go back to the rule on conditional probability. Okay. Refer to your table of values so that you know exactly which numbers are you looking at. All right. And then there, you should be able to get your answer. For this one, for the intersection, you just have to count what's the probability of getting a 3 all the way to getting a 6. You should get 13 in total. Okay? And then that is how you do example 18.